Hello and welcome to this next video on the series Introduction to Radiation. We're going to cover today lots of things such as ionizing density, distance travelled by different radiations, uses of radiation and detectors of radiation. As always, I'd like to thank John Sharkey for his flash learning materials. Before we go any further, I want you to remember and revise the structure of the atom. Remember, in the center we have the nucleus, which contains protons and neutrons and is positively charged because the protons are positively charged, the neutrons are neutral, and round the edge we have electrons represented by these small red blobs. Remember, in an atom the number of protons equals the number of electrons. Alpha, beta and gamma are called ionizing radiations because they produce ionization in the materials through which they pass. Energy may be absorbed from alpha, beta or gamma by the material, and we saw this in the video of the material by furry elephant. When an alpha particle collides with the atom, an electron can be knocked off. The alpha particle transfers energy to the electron and the alpha particle slows down. Do alpha, beta and gamma cause the same ionization? First, we need to clarify the question. A cloud chamber can be used to investigate ionization density. This is the ionization produced for each millimeter along the path. Here we have an alpha source. Notice the paths are short and thick. The tracks are short and thick because the alpha particles are large and collide more easily with the air molecules. When we replace that with a beta particle, they are smaller and make fewer collisions than the alpha particles. During their collisions, beta particles are likely to be deflected, hence the lines are more scattered. Gamma rays have no mass, hence there's very little interaction with the air. They produce very few traces in a cloud chamber. Alpha particles produce greater ionization density than beta or gamma. Alpha and beta and gamma require different materials and thicknesses to absorb them. Alpha particles are absorbed by a thin sheet of paper and travel a few centimeters in air. Beta particles are absorbed by a few millimeters of aluminium and travel a few meters in air. They can pass through paper. Gamma rays require several centimeters of lead to be absorbed. Even then, some of the gamma rays will pass through, as you can see in this animation. Gamma rays travel many kilometers in air. Several meters of concrete will stop most gamma rays. Radioactivity is invisible, has no smell, makes no sound. In fact, it cannot be detected by any of our senses. However, because radioactivity affects the atoms that it passes by, we can monitor it using a GM tube, photographic film, gold leaf electroscope, spark counter, cloud chamber, bubble chamber, and modern detectors. The Geiger-Müller tube is probably the one that you'll be most familiar with. The Geiger-Müller tube with a counter attached gives you the number of particles detected per minute. GM tubes work using the ionizing effects of radioactivity, so they are best at detecting alpha particles. Photographic film was discovered in 1896 by Henri Becquerel. Radioactivity will fog photographic film. We can use that in the old-fashioned film badges worn by nurses and radiographers. The gold leaf electroscope is a piece of apparatus you might have seen in the lab. It can also be used to detect charge. The spark counter is a very old form of detector. Again, because it uses ionization, it works best at detecting alpha particles. The cloud chamber you might have seen in other little video clips. This is just an animation. Here is a video clip of a real cloud chamber, although the quality is very poor. Hopefully I'll get a chance to show you one of these when you're back in school. Alpha and beta leave trails in the vapour. Here are the trails here. Remember that radioactivity is a random process, so you can't predict where you'll see the trails. A similar idea to the cloud chamber is the bubble chamber. Particles leave trails of tiny bubbles in a liquid. And these are the original ways that they detected ionizing radiation in particle accelerators. All this material is available from darville.clara.net. darville.clara.net has great resources on uses of radioactivity. As you can see, uses of radioactivity include smoke detectors, thickness control on such things as paper, aluminium foil, etc., etc. Radiation can be used to sterilize materials and fruit, such as medical equipment and strawberries. Radiation can be used to date old plants and animals. So radioactive dating is not about going out with a partner, but aging materials. Radioactive tracers can be used for medical purposes to check on the health and well-being of people. They are also good to find leaks in pipes. Radiation can be used to check worlds and check cancer treatment. A medical syringe is pre-packaged. Which of the following could be used to sterilize the syringe? Alpha particles or gamma rays? You must justify your answer. Please pause the video and write down your own answer. The answer would be a beam of gamma rays would be used because these will penetrate, i.e. go through the packaging and kill any germs or bacteria. Alpha particles would be absorbed by the packaging. Question 2. A radioactive sample emits ionizing radiation. A Geiger-Müller tube is used to detect the emissions. The count rate is shown on the rate meter here. Here's my sample, here's my Geiger-Müller tube, and here's my rate meter. A piece of paper is placed between the source and the detector, and the count rate has decreased. A thin sheet of aluminium is placed between the source and the detector. The count rate does not change from what it was with the paper. A thick piece of lead is placed instead of the aluminium, and the count rate reduces again. Explain which of the following ionizing radiations, alpha, beta, or gamma, is emitted by the sample. By the way, there might be more than one. Please pause the video, write down your answers, and we'll go through them. The correct answer will be that the sample emits alpha and gamma. Paper absorbed the alpha and it went from 480 to 220 counts, almost half. When we added the beta, it made no difference. So alpha particles would be stopped by the paper. The beta particles, there aren't any, so even though we replace that by aluminium, because there are no betas, there's no change in the count rate. When we added lead, the count rate reduced again, showing that lead absorbs most of the gamma. This background count of 45 counts per minute will be due to the background sources all around us. Now please go to your class notebook and answer the questions on more on radioactivity. Question 1 is a mix and match where it gives you a use of radioactivity and an answer. Going down, if I can, question 2 is about the range in air and the range and what's stopped by the types of radiation. And question 3 is a reminder of ionizing radiation. There'll be another sheet on detectors of radiation for you to fill in and mix and match. Please complete these. That is your task for the 2 weeks. Thank you very much.